Oh, that's neat. Sightsaver cleaning cloth for my glasses.
She ended up with your coat.
How you like that?
Everybody have a...
She had a black leather coat, and one day she ran out for lunch and came back, and when she came back, she hung her coat in the closet.
Yeah.
Well, she got ready to leave, she couldn't find her.
Hey, what's the bad?
She looked through all of the
Never been in
she
there?
Where
Where is it?
Oh, my goodness.
Buy all your clothes in the background.
Huh?
Buy all your clothes in Eastern Mountain, King Power, Northern Reflections, or that one. What's the...
Come on over here.
American, that's it. American Eagle outfits, yeah.
I don't think that will.
I'll leave it closed.
Oh, no wonder there's a wall.
Go with Bonnie.
The only time I go to the mall is when I gotta fix knee on or something. That's
Tell you what,
right up down there.
couple of Levises.
Backpack? What's in the backpack?
Grandma!
Backpack, pack baskets.
Everybody's snapping pictures, smile.
Take your watch.
Now you can start taking an ironing.
Merry Christmas.
He had a tank base like that. It was probably as wide as a table and 3/4 of length.
They say that the heart always goes home at Christmas.
No kidding.
And I'm lucky because my heart goes home.
Yeah.
Thanks for making home such a special place to remember and to go back to. Not only at Christmas, but every time I think of you. Merry Christmas. All your children, your grandchildren, and all their families. Thank you, everybody. Thank you all, everybody. Thank you. Thank
Merry Christmas.
you.
One lady I heard of, she's got pictures.
This is what I need.
Show ones, most likely. We were up there this summer, I saw some of the sea guys.
Getting it all right?
You make some? There you go.
That one's next, yeah.
When he was a boy, everybody made them.
When we get to that one, you can help me. Oh, I opened this upside down. Wouldn't you know? There's the bottom.
They all do that lately. I don't, maybe so you can do exactly what you're doing. Everything, all the blankets are in the box upside down.
Another one, he said,
What? So maybe it's so you can just shove it upside down and take it back.
don't take no orders or nothing. Some of them are almost straight. Some of them are real nice. That's the, that's the original, that's the old class.
You know what we're gonna make with this? Coffee. Let's pull it over here. See what we got. That's it. Here's some more.
Wait a minute.
I don't know. We gotta look and see what's in there. Pull. Push on it. Push on it. There. We got it. See? Oh, we got paper. Just a lot of paper. What do you think is in there? What do you think is in all that paper? Whoops. What's that? I don't know. Let's go look. I don't know what that is.
Are you kidding? He's got tips from the end of Meadow Grind.
Dishes? I don't know.
No.
Got wire on it.
No. There you go. What is it?
New light fixtures for out in the store here.
Oh my gracious!
New light
Oh,
fixtures for here.
goodness sakes, beautiful.
Kind of look like the old ones that used to be out here.
Yeah,
Going
yeah, like
modernized.
the ones we had years
Yeah,
ago.
yeah.
Oh my man. Oh, that's great. That would be good.
Nice if you turn light on.
Now, what do you think is in here?
Lights, anytime you score a goal.
Toys? Yeah, we gotta look for some toys.
Wow.
Look what I see. Oh my goodness. Look what I see. Isn't that pretty? Oh, that's nice. Oh, wow.
That's nice.
That's beautiful. Look at that. Very pretty. And the slats to go with it. Wow. Look at that. That's nice. That's pretty outfit.
We should have brought one.
That's cute. That'll go with anything.
For who?
Oh, yeah, you would have
Very
tried.
much.
Who does?
Is that? Oh, yeah.
That's so that's nice.
Jam side.
How long ago?
You sit there and jam, give it a few beers, and sit there and jam it He goes for walking. Give me a couple of beers again. Nice Pepsi beer. You don't even know. No.
Dad,
Dad.
your son wants you.
What? Oh,
That's your stew, Ma. Go ahead.
He listens to you.
just put pop on you?
Aiden doesn't count today or what? He's been calling you for the last half hour.
He doesn't pay attention to me, I don't pay attention
What?
to
What
him.
do you want?
Professional courtesy.
No, you go, you press it right here.
Oh,
Here's
this is
your books.
nice walking cane.
That's your walk. That's your
Oh,
walk.
wasn't that
That's
nice?
your walking stick.
If you get stuck, we get snow treads that go on there.
Can you get spikes so when she goes ice fishing?
Yeah, that's right.
Yes, put spikes on her for ice fishing.
Get summer, take it over to Bob and put the summer tires on.
Oh, that'll be nice.
How about slicks for when she jogs?
Hey, Danielle, there's nothing, it's just paper. Inside, yeah.
What did you do to your shirt?
Want the adjustment, David?
How are you?
Pop me in on this. Oh, you'll have to get Cindy to pop me in on how to use it.
Yeah, don't you have something by anyone?
How high is it supposed to be?
Well, so you can,
Lose your balance, it's there to catch you.
But I think like anything else, you're gonna have to get used to it.
Yeah, you won't get used to it because there ain't gonna get, after this snow's over, you ain't gonna even need it again.
hey, watch your mouth.
We ain't getting no more snow.
Hey, no more ice and
No
snow.
more ice and snow. This is it. This is it.
That's a good height, I think, right there.
I'll try it for a while, and if it seems
Yeah,
like it should,
try
we'll
it, if it ain't
change.
right, we'll lower it.
Talk to your friends.
Huh?
Talk to your friends.
Yeah, see what they, how they manage, yeah.
Play it. Play it, he said.
I think,
Ken, you play that good.
well, thank you all very, very much.
You're welcome.
My goodness, as usual, you do too much. It certainly is wonderful, all these things here. Iron and coffee pot and dress.
Well, it's just saying, you better get some work done. Then you
Christmas, we wish you a Merry Christmas. We wish you a Merry Christmas and a Happy New Year. Wish you a Merry Christmas. We wish you a Merry Christmas. We wish you a Merry Christmas and a Happy New Year.
All the cameras.
No, that would make a good picture. It would.
Take a picture.
Oh, yeah, yeah.
What I have is a lot of information to go over, but Jerry said I could have all the time I wanted, so, I mean, he said I could go till 6 o'clock.
No, I said you go till 2 o'clock.
And I put an agenda in front of each of you, which has some of the information, so you won't necessarily have to write a whole lot yourself. I did that for Craig.
Thank you.
But we're not gonna give we're not gonna give one of these to Ron, because if he had some phony excuse to skip out of here, so we'll just leave him in the dark.
This is what it looks like, Ron.
Okay, first subject on the agenda is polymers. And Jerry always asks, so we always do it over again, but maybe we get better at it with time. Polymers is a subject or a word that covers an awful lot of ground. And of course, we're always talking about water treatment polymers, but there are polymers used in a lot of things, you know, in plastics and floor sealers and waste treatment. In other words, polymers is a word, as it says there, a macromolecule, which is just a large molecule, and it's an organic molecule usually because it has the CH and O's in it, but it has a lot of repeating units. In other words, you can have a compound or a molecule of all kinds of inorganic things, and it has a rather limited, like calcium chloride is 1 calcium and 2 chloride atoms combining. But in polymers are chains of repeating units, and then they'll have maybe what we call functional ends here and there where you can attach on other things, and they will a lot of times have charges on each of their endings. A lot of times what you'll see is they're made of repeating, like methyl or ethyl groups. Methyl is CH2. And then maybe it'll have some other things here and there on it. But this can go on for great lengths. And polymers are really engineered. They can be created to be certain lengths. They can be created to have certain other compounds added into them. There's some pictures right at the bottom of the first page, but those aren't really polymers, but they're close or similar. But it shows you some endings that they could have on them. Maybe you're familiar with, let's see, a typical molecule, like I'm gonna do this off the top of my head maybe, but calcium phosphate, for example, has a sodium phosphate, something like that, has a molecular weight of say 100. Well, these polymers, because they can be so large, can have molecular weights of in the millions. And they serve a lot of purposes by the fact that a polymer can have a whole lot of charges, like negative or positive charges. Generally, they're going to be negative charges. They can also, because of their heavy weight, they're used a lot of times in wastewater treatment to do a couple different things. A lot of waste materials might be positively charged, and they will hook onto the negative charges on the polymer, plus all that mass of weight helps settle them out, so they gather in or collect a whole lot of things. So polymers that we use are going to have slightly different purposes, and their functions are to act as dispersants, scale inhibitors in boiler and cooling water treatment. And as dispersants, and And you'll see under mechanisms, well, we'll start right down the list. Sequestration, which is referred to as solubility enhancement. This prevents precipitation. Now, a lot of times when we have calcium or a hardness ion in our boiler water and we combine it with a phosphate, it precipitates out a solution. You've got a calcium, it's a metal ion that has a positive charge on it, it's in solution. It finds this phosphate ion, which is negatively charged. They combine to form a molecule, two ions combine to form a molecule of calcium phosphate, which precipitates. Similarly, calcium carbonate will form. And of course, in a scaling situation, those crystals build on each other, so they become visible and form scale, and a lot of times will adhere, of course, to our heat transfer surfaces. Different things cause precipitation. The calcium has a solubility that's is reduced by higher pH. So the calcium ions that are dissolved in the water to start with, when they hit the boiler and they're heated up, they precipitate out a solution. Well, a dispersant prevents the polymers, because they are charged, they tend to adhere to the surface of this crystal. You make a calcium carbonate crystal, and the dispersant will prevent those things from building on each other, and they keep it in a dispersed form so that they cannot coat out or deposit out on the metal surfaces. Go ahead.
How does that relate to the sequestering?
Okay, I went ahead of myself. The sequestering is really a chemical reaction. It'll have the original sequestering agent, really, or the oldest one, is like polyphosphate, which would combine with, but they'd stay, it would prevent it from precipitating. It would have like a chemical bond that would keep it, I always call it holding hands, so that it works its way through the system and down the blowdown or whatever, without precipitating out as a crystal. So that's what the sequestering action. Now the polymers do all of these things. They act as a sequestrant. They act as what is called a crystal modifier. It'll because of the way it forms on the surfaces, it'll, instead of a nice clean flat parallel sided crystals, in fact, there's nice pictures in a number of books. I don't think I've shown those before, but you know, they have these microscopic pictures of these molecules, and they will be irregularly formed. In dispersing, you're preventing these crystals that have precipitated out from being able to agglomerate and form bigger chunks. Crystal modification, of course, takes those crystals and gives them small, irregular, readily fractured surfaces that do not adhere to each other. I always draw the picture of crystal buildup. Normally, on a heat transfer surface, you get these nice crystals, calcium carbonate crystals, that form on the surface, and they keep building here, and you get this hard, dense scale, which is very difficult to remove once you've got it. In crystal modification, it causes the crystals to be irregular shapes, and when they get here, there'll be air spaces between them. The bonding, the surfaces that electronically, electromagnetically bond to each other. Well, they get up here like this, and because they don't fit together well, the flow of water, they fracture and they fall apart. And this is especially true where you have some agitation. But it just won't build up as a scale. It stays as a loose, more flocculent type sludge that gets to,
Wants the car keys probably.
Okay, these, I really should have brought the pictures. I just assume, I've seen so many of these that I just assume everybody has seen the pictures in the textbooks of how those crystals are deformed, so they can't build on each
We
other.
have at any rate, because it's part of Jerry's seminar, he has some pictures in the literature that he hands out, which we've been through, and I don't think Pat's had a chance to yet.
This is what the water treatment polymers do, all of these things. Now, there are different polymers that do different things better than others.
I still don't have a grip on the sequestration though.
Okay.
I didn't quite,
Okay.
I understand that
Okay, when you
the
get down
solubility
to crystal
enhancement, but how?
modification, you've allowed the thing to precipitate out a solution, so it's not measurable on your test anymore. But it'd be similar, sequestration is similar to chelation, where you have just the two molecules. The one, well, it'll be more than that, but to simplify it, the polymer and the calcium combine, like instead of calcium sulfate or calcium carbonate, you got a calcium poly something or other. And that, but it's still in effect considered like in the dissolved state.
It isn't heavy enough to fall out.
Yeah.
Is that,
And
would
it's
that
not
be a good way
going
to put it?
right. It prevents it from precipitating out, which is the first step of making a deposit. Now, obviously, when you make a calcium carbonate molecule, you can't see it. It's that small. That it has to, before you can see it, and of course, before it gets fat in your tubes, where you can really see it, you've got billions of these things that have crystals that have formed on each other. Maybe when you were a kid, you did that supersaturated solution and let it sit very still and watch the crystals grow. And you'll get those, you've seen in the gemstones and things that are really quite beautiful that are crystals. And those are all molecules that have stacked very neatly on each other. And are very, give you that clear, light goes through it type of thing. Whereas what the polymers do is they interfere with the ability of these calcium carbonates to combine with each other in a nice, hard, dense state. And so, in other words, we modify these crystals so they can't build on each other, and then we, by charge, act as a dispersant at the same time, because the calciums that show up here are positively charged. Our polymers that we use, like polyacrylate, are anionic polymers, which have a negative charge. They combine with it, but then you create a whole bunch of, these polymers have all these charges all over that collect all these things, but then they have, because they have an excess of negative charges, now all the particles become negatively charged and they repel each other, and that's how the real function of dispersion is. It breaks them up and keeps them from agglomerating, coagulating together. Now, in the old days, we did things a little bit different. We let the calcium phosphate precipitate out, and we had some natural polymers like tannin, lignin, starch. The original water treatment product for boilers was potatoes. The starch in the potatoes was that's where the lignin comes from, and the tannin. Those things were sort of natural organic polymers that essentially did some of those things that these synthetic polymers that they create. Okay, down here in E we have water. What are the polymers we use in water treatment? Now there are an awful lot of them, but they fall into a couple basic categories. The homopolymers, the original was that they discovered would really work well in boil water and cooling water was polyacrylic acid. And PAA is the way it's written a lot of times. Polymethacrylic acid and polymaleic acid. And these are called homopolymers because the functional end, and it'll look, I don't have those drawn, but it'll look something like this, but it'll have, on the end, it'll have a carboxyl group, which is like COOH, something like that on the end. And that's what does all the work. know, you make this big molecule so you can stack these things on it, but it has one functional group, and that's what a homopolymer is. Okay, there are the, so you see carboxylic acid, that's what the working part of polyacrylate is. And polyacrylate is probably the most common. That's in many. You'll see it on, when you see formulas or ingredients on a label, a lot of times you'll see sodium polyacrylate, which is how you get, you know, these polymers come as acids. They're organic acids. They're not usually strong acids. They're called weak acids, actually. If you see polyacrylic acid, this is just kind of like it's almost like a clear syrup. It'd look like a very light pancake syrup. Might be a little gold, but it's viscous like that. But what happens in water treatment, if you look at the label on the drum, it'll say sodium hydroxide polyacrylic acid. Now, if it says that, that shows they haven't neutralized. But a lot of times they just write sodium polyacrylate, because what we do is with the caustic that you see on the label, you're taking polyacrylic acid and neutralizing it with the caustic. It becomes sodium polyacrylate. It doesn't really matter still what it does in the water that counts. There's a sulfonic acid functional group, and there's another one that I couldn't think of the name of, that when you get down to, okay, step to copolymers, this is where you have two functional groups. You got the same kind of molecules. Incidentally, polyacrylic acid is used usually in a range of a molecular weight of 2,000 to 5,000. How big the molecule is sometimes makes a difference too. And when they make polymers, molecular weight is where they try to fit it in. In other words, they know that at a 2,000 molecular weight, polyacrylic acid works best. But when they're making the batch of polymers and trying to polymerize all these methyl or ethyl groups, what happens is they can't quite get them to all occur at the same time. So you'll have like a little bell curve where the average is 2,000. And a lot of times they'll consider that if it's not a very narrow bell, you've got a lot of slop to it, you've got some wasted polymer in there. I mean, you've got polymers that aren't doing it as good. So supposedly this is what the good manufacturers tell you, that they keep theirs, they have a very narrow range of molecular weights. Copolymers, again, where you have two functional groups, these are become extremely important because this is where you get the best iron and phosphate control. The polyacrylate and the polymaleic acid are two very common homopolymers, and they're very good at scale control, but they're not very good at taking care of iron or calcium phosphate. The fact of the matter is, some iron contamination in a boiler water, for instance, kind of defeats the polyacrylate somewhat, so it doesn't work as well. So it's extremely important to have these copolymers in there to take care of calcium phosphate or iron oxides or iron hydroxide or whatever. So in our products, especially boiler water treatment, you'll almost always have at least two polymers in the formula. So you get the homopolymer and the copolymer. Number 4 there, it says terpolymers. This is where they now have the third functional group. And of course, this is supposed to be a little bit better. We have played with some terpolymer that Roman Haas makes, but not really too wild about it. It's very expensive and it doesn't do that much more. And we get such good results by combining one or more of these other, 2 or 3 or 4 of these other polymers that I haven't been convinced of the need for that yet. Flexibility, I just want to point out that these polymers are so good at what they do, and they can handle so many types of situations.